Can you hear me?
Yes.
Yes.
Okay.
Loud and clear.
So how about last
Loud
week?
and clear.
Last week we already studied the introduction, which means the function of 2 and 3 variables. And then we study limit. But for limit of function of several variables, you already saw that there is a principal difference between this function and function of one variable. For two variables, the idea actually is the same. It is the distance between a point and a fixed point and the variable point tending to that. Then the image of the point or value of function is close enough to a given value L. That's the idea. For one variable, the distance is modulus of the difference. But for several variables, this is distance is computed using the Pythagorean theorem, right? Distance of 2 points in the space R2 and R3. So, however, for several variables, we have very interesting result to prove that the limit doesn't exist. So it is about the path limit, which means if you can find two paths C1 and C2, C1 and C2 both passing the point I say P, and you have different limit of F when a point M tend to P, but M belong to C1, and limit of F when M tend to P and M belong to C2. If you have a different limit, then the given function has no limit. Okay, that's important when we have to show such a result. And after limit, now we move to the continuity and then to the next part, which is quite new for you. Partial derivative. In Vietnamese, we say đạo hàm riêng. But in the North, we don't say pronounce correctly. Should be đạo hàm riêng, right? However, when this is the tradition in the north part of the country, except some people in Nam Định, for example, they always pronounce R very correctly. So today we study the part 4 and part 3, and next week the last two parts and finish chapter 1. Now talking about the limit, we understand that we can use the passing to continuity, we can use the limit, which is, so look at what I write. When you have a function of one variable, and then we want to say that it is continuous at a point A, then we look at the limit. X tend to A must be equal to FA. So this definition for one variable is characterized by three conditions should be true together. First, we talk about F at A, which means that A must be in the domain of F. Otherwise, you cannot evaluate FA, right? Next, we talk about the limit, which means that there exists the limit fx, x tend to a, and we denote it by some value L. And the last one, limit equal to fa, which means that you should have L and fa are the same. When you have all three these conditions, you have a continuity of fx at a point. And if either of these three conditions is violated, you have no more continuity. But either of these three conditions is violated, means that you need only one condition which is wrong. Not all, one enough. But which one? So then you can see, as I write priority, first you check whether A belongs to D or not. If A is not in the domain of F, it's gone. Don't have to do anything. You conclude that function is not continuous at A. If it is okay, you look at the second condition, whether limit of fx extend to A exists or not. If not, gone. No continuity. No need to consider the last one. But if yes, you should compute the value of the limit and check the last one. If the last one is right, you have all conditions are satisfied and continuity you get. But if the only first two, we already verify it is true, and the last one is wrong, then again you have no continuity. Okay, so such a thing, and we do exactly the same, but from the point of view of two variables or three or more general n variable. Suppose you are given a function fxy, and you know the domain of this function is D, which is in R2, because the function of two variables. Every point at which function is defined belong to some set of R2, and all points at which f defined perform the domain, right? And here, this point, we want to consider continuity at this point, then the first, this point must belong to, to the domain, exactly the same as the first condition I already mentioned for one variable. Pay attention, for limit, you don't need to have such a condition, right? But for continuity, you must have it. Then a function is said to be continuous at this point, AB, if limit fxy, xy tend to AB exists. So this is the second, corresponding to the second condition for one variable, and equal to evaluation of f at AB. So this is the last one. So you see, again, we have all three conditions which must be satisfied to have a continuity at a point for several variable function, exactly the same as one variable. Only situation is now, at least in this definition, two variable. Okay, here what I already explained, I wrote in the slide. Continuity at a point, you need three conditions. Okay, f is defined at this point, which means that this point AB belongs to the domain. There exists the limit as a point tend to that AB, and value are the same, value of limit and value of f at AB. So exactly the same, okay? So, and if a function is continuous at each point of D, or you can write at every point of D, every point of D, then we say that f is continuous on this domain D. Okay. Now, we should look at two classical and important elementary function of at least two variables which are continuous everywhere if these functions are well defined. The first one, polynomial. Polynomial of two variables is a function also two variables, but this function pxy, right, two variables, is of that form. So you see here two variable function of two variable, but it doesn't mean that all two variable must be appeared in the formula. For example, C0, no x and y are involved, but you can think it is a function of two variables. The value is C0, but it is for all point x, y. You always have such a thing. This is, what is that? A constant function, right? A constant function. Then it is function of two variables, which should be understood, but value is constant. The same for here. Gxy is C1x, or somewhere I write here C2y. You see, either of variable y and x are missing, but it's no problem because we talk about a function of two variables and the value depend only on one variable, etc. So here no y, here no x, but that one you have both x and y. So which means in general the formula here, polynomial, contain all terms like that. N and m can be zero, non-negative integer each term. So this is polynomial, okay? For example, here, you have constant depending only on x, depending only on y, and depending on both x and y. So this form of function is called a polynomial. And you can see this polynomial is continuous at any point of R2. Okay, that the other function is rational function. Rational function, as for one variable, this is a ratio of two polynomials, but now polynomials are of two variables, pxy over qxy. Of course, denominator must be non-zero to have a rational function when defined. So for example here, numerator is polynomial, denominator is also a polynomial of two variables, but we need the condition y and x squared are different to have the function when defined. Again, this rational function is continuous at every point at each it when defined, which means that at on x and y, on x and y, for which y is different from x squared. How and why can we claim that polynomial and rational function are continuous where it is defined? Here, we use first this limit we already talked about last time, which means this function for any m and n non-negative, which means that bigger than or equal to 0, m and n, is continuous because this satisfies all three conditions or satisfy the definition of continuity. And then you consider and you apply property of the limit, which means every term a function of two variables which are continuous at a point AB, arbitrary point on the domain. And domain here is whole R2. And then you take the sum. Actually, the sum of continuous function is also continuous because when you consider the limit of the sum, you can be sure that it is the sum of the limit and you get the answer. So that's why polynomial is continuous everywhere because it's defined everywhere on R2. The same for rational function. Here, limit of the quotient is a quotient of the limit provided that the denominator is non-zero. So you get again using the definition, right? So that's why now we have to claim important. Polynomials are continuous everywhere on R2. And rational functions are continuous on their domain of definition, which means are continuous at all point at which the rational function is when defined. When defined, in this case, is the numerator is okay. This is numerator, but denominator must be non-zero at this point. Okay. Here, yes, everywhere we talk about continuous, but that one rational function only at a point x and y for which y is different from x squared. That's the two important continuous function. So, example, you are asked to determine whether this function gxy is continuous at 0 or not. The origin of coordinate. You should pay attention that this function g is given in two formula. If a point xy is not the origin, you have this formula. But in the case a point is the origin of coordinate, you have the other. It means first, function gxy is defined everywhere, everywhere on R2, everywhere. Okay, but you are asked not to look at everywhere point. You are asked to look at only the origin, because actually, if a point x and y is not the origin of coordinate, then x squared plus y squared is non-zero, actually bigger than 0, right? Not the origin, then at least one of the two coordinate x and y is different from 0. Then sum of square must be non-zero. And in this case, you have the formula rational function, denominator is non-zero, then you have continuity, as we talk about here, right? So, which means for this point, you have a continuity, So the rest is only the origin of coordinate. The question is, how about this case? So this case, you should use the definition, which means evaluation of function is 0 at this point. So that's why we see a point 0, 0 belong to the domain, because function is defined everywhere and value is 0, right? And at least you have the origin is in the domain and value at the origin is 0. So that you have to check here. Already condition 1. Here condition 2 and condition 3. Condition 2, limit exists. Condition 3 equal to L. L here, right? So you have to check. However, we already proved last week that the limit, this function doesn't exist by providing two paths, C1 and C2, different and passing the origin. And you can check the path limit or limit along these two paths exist and different. So this function G has no limit. Has no limit. You don't have such a situation. Don't care about that. It's gone. Second condition already wrong, right? Doesn't exist. So which means this function in example 3 is continuous everywhere but. So remember the English grammar. G is continuous everywhere or at all point, but the origin or you can replace by another word, except the origin, except at the origin. Okay, that's the English way to talk about. Sometimes the student confusing all but one, which means that except one. Okay, so that continuity. Now we move to more important part, partial derivative. You understand that when you have a function of one variable, you can look at the possibility of the existence of derivative of f at a point A, f prime of A. So talking about derivative, this is derivative, right? of the first order, right? First order. You can also have f prime, f triple prime, etc. So, but at least you understand that talking about derivative, which you must remember the word rate of change. Talking about rate of change, you understand that we talk about the derivative. Yeah. So what is that? This is the limit fx minus fa over x minus a, x tend to a, right? Or if you denoted x minus a is a h, then this is the same as f a plus h minus fa over h tend to 0. So they are the same. You understand, right? But it is one variable. How about several variables? So for example, two variables. You have two. What to do? What to do in this case, right? You should think, if we fix one variable, either x or y, then you can get a function of one variable, the other variable. So it is a function of x, and y is understanding as a constant. This is a function of one variable. Then we can talk about the derivative. The same if we take x as a constant, and then we look at y, you have a function of one variable y, and you can think about the derivative. And these two derivatives, and of course, higher degree, higher order, we call partial derivative. Partial derivative, right? Okay. So then we have the definition. Partial derivative of f with respect to x, with respect to x. What is that? We denote it by f subscription x. It means partial derivative of f with respect to x is understood as the derivative with respect to x of the function when we keep y unchanged as a constant. Unchanged. So you see, I keep the same y, understanding it is a constant, and I look at ft minus fx over t minus x, right? Exactly like that. And you take the limit as t tend to x. If limit exists, we say that a function f has a partial derivative with respect to x. And this subscription indicates that the value or variable we want to do is x. Okay, not fx. You have another notation. This is the same as df over dx. But remember, this one is a curly d, not normal d. Not normal d, because normal d, when you write like that, which means you have f prime of x, one variable only. For one variable, you use normal d. to indicate the differentiation. But for several variables, you should use curly D. You are not allowed to write for function of variable these things. No. Because this is for one variable. You should write in curly D. Okay? So what is that? This symbol means that the partial derivative with respect to x and evaluated at a point A and B. That is because partial derivative with respect to x, you keep y equal to b here is y, right? Unchanged. Only t vary. Okay? So the idea and illustration, when you keep y equal to b, so what is that? This is the graph of a function of two variables in R3. The graph. Okay. So when you take y equal to b, which means that you already consider the cross section. It is here. We talked about in calculus 1. Here, that cross section. And you get the intersection here between the graph and the plane. This is plane. That's the cross section, right? So such a thing, we want to look at the direction and x run freely. Okay. So in this case, when you consider the cross section, you have the blue line here. I override by red, but actually I should change if I want to some color, but it's okay, right? No problem with that. So you have a curve and you consider the tangent line. See, tangent line to the curve on the direction of x, because y is fixed already. Yeah, y is b already. And then you get f right, the slope, right? Slope of the curve. Okay. Yeah. You know that derivative of a function of one variable is a slope at the point of tangency, tiếp điểm. A slope of the straight line, you know. And here, you should understand that because we talk about one variable, along the cross section of the plane y equal to b and the graph of the function, you have the slope of the tangent to the curve at this point. Okay. And also, as I mentioned, talking about derivative, you understand that you are talking about the rate of change. A rate of change along the positive direction x, right? Here, that positive direction, see? That one, here. That positive direction to R plus, to R, positive, right? At a point. You have other also the notation. Fxab means that partial derivative with respect to x at a point AB. You can also think about fxxy restricted when x equal to a, y equal to b. This is the same. Or you use curly D. df over dx evaluated at x equal to a, y equal to b. because this df actually the same in different writing. So for example, you are given this function and you are asked to use the definition to compute f prime with respect to x, y, or we write fx, or we write df over dx. That one. Yeah. See? Easy, right? Because you want to talk about the derivative with respect to x, then you must keep y unchanged as a constant for x. Constant for x, not in general, no, constant for x. So then we can do that one. We keep y because you are asked to use definition. Keep y. And then you consider ft minus fx over t minus x. Of course, here f, we understand that we have y fixed. And what is that? Here. And then you take out y cubic out of the limit because it is a constant for x. So you have this one and limit, you divide it, you get this, and the answer is 2xy cubic. And then you understand very easily to do like this. F is x squared y cubic. Then f prime is derivative of f. Derivative of f the derivative of f. Where that? Oh, it gone off. Okay. Derivative of f. Here, you can see, you can work on a function. See? You can work on a function. Understanding that y is a constant. Then x squared y cubic derivative with respect to x is first I take out a constant and the rest I consider the derivative for x, which means that 2x and 2x together with y cubic, you get 2xy cubic. That's very easy to see, right? So the same for this case. At 0, so this function similarly to gxy before, define everywhere and no more rational function because psi is not rational function, but it's when defined. The question is whether you have to determine whether the limit exists because this is derivative, right? So, and if yes, how to find the value? So at 0, a equal to b equal to 0 for derivative of with respect to x, you should take b equal to 0 at a constant. So I put b equal to 0. And the rest, I consider the quotient ft f0 over t minus 0 because this is derivative. And I find the limit. The limit here is now limit of one variable t only. This is psi t over t. T tend to 0 and h equal to 1. So then the answer is yes, it exists and equal to 1. That's example 3. Okay? So similarly, You can do exactly the same for partial derivative of f with respect to y. Exactly the same. Subscription, in this case, you keep x as constant. You work on the second coordinate y, and here t tend to y, keeping x as a constant. Exactly, you replace, you change the role of x and y in the definition, previous definition, you get this one. Okay, again, subscription indicates that the value when you consider t tend to y. Okay, so again, this you put x equal to a because you look at partial derivative. Okay, so and then you get again, you get a slope. Interesting, exactly the same, but now the slope of the tangent line or rate of change along the direction y direction, because you talk about the partial derivative with respect to y. And notation here, see, that one, or curly D. Only remember, you work on variable y, not variable x. And again, the picture like that, cross section, the blue is curve and red is tangent line. So everything is clear for partial derivative with respect to x and with respect to y. Okay. You can also change to use h instead of t tend to a or t tend to b. In general, you can change to h exactly the same as we did for one variable, but only direction different, right? Here for fx, here for fy, we use the same h tend to 0. And denominator must be x plus h minus h, which is h. Denominator y plus h minus y, which is h. So very clear. Cannot be confused, right? So how about three variable? Three variable is the same. You want to talk, you want to compute, you want to consider partial derivative if with respect to x, then you write x in the subscription. And because with respect to x, y and z, you should keep unchanged and as a constant. Only x is a variable, right? Regarding y and z as a constant and differentiate with respect to x. That's the thing. And n variable, the same, which means f differentiates partial derivative of x, partial derivative with respect to y and z, right? And more general, n variable with respect to xi, for example, which means own coordinate are are fixed as constant except or but xi. But xi, tức là trừ cái thằng xi ra, còn tất cả các cái biến khác constant, consider as constant, nên chỉ có úp đối với lại xi thôi. thì các em sẽ được là đạo hàm with respect to xi, partial derivative. Okay? So, and notation. And sometimes you write not fxi, you write fi. Understand that this is with respect to variable xi. Okay? Evaluating easy, which means you consider the partial derivative in general and evaluate it at a point. Then you get the answer. So now you understand how to compute the partial derivative of function of several variables. You must recognize and determine with respect to what variable you are asked to do. Then you fix all other variable as a constant and working as one variable, function of one variable with respect to that variable. Okay? And then for working with x only, you can apply the rule of one variable differentiation. We study in calculus 1. We fix other variable, we work on one variable and we use the properties of differentiation of a function of one variable. Then it works. Okay? That's the same for x, the same for y, the same for z, or other variable in several function, a function of several variable. Okay? So we stop at this point. And after that, we start to look at example 7. Okay? Now a short break. A short break. 5 to 10 minutes, maybe 10 minutes to you, so more flexible and free for 10 minutes. And then we start at, now 8 minutes at 11:25 as usual, the next hour. Okay? So, short break. So we continue our lecture. So lecture today is shorter than previous one. And next week, the lecture is longer than the usual. The reason is I want to stop at the section 4 before we move to the last two sections, chain rule and the application, approximation. I don't want to start something new and keep it the unfinished to a long time, right? So that's why I finished today's lecture at about 12:05 or something. And then next week, maybe we should continue to reduce the break between two parts to 5 minutes, not 10 minutes, and maybe some minutes at the last lecture. The last time I tried to speak a bit faster, or I ask you to read by yourself this or that part. But in general, so the chapter 1 is still okay. More interesting is chapter 2. So now return back to our lecture. We already study what the partial derivative of a function of several variables, two variables in our case, with respect to x, with respect to y, and how to evaluate it. Now the example. You are given this function, and you see you are asked to compute, or we write evaluate the partial derivative at the same point, 2, 1, x equal to 2, y equal to 1. For this case, as we already knew, we start from the formula of xy. X cubic plus x squared y cubic minus 2y squared. And if we want to compute the derivative, partial derivative with respect to x. So this one, with respect to x, you have 3x squared. This one, y cubic, is a constant. Then we should keep unchanged. And then x squared derivative is 2x. Minus this one, no x. Constant with respect to x, derivative of a constant is 0, which means that you have 3x squared plus 2x y cubic. And now, when you are asked, you are given a specific point, which means that you should look at this formula and at a point 1, 2, which means x is 1, y is 2. So which the same as you write, but for working, you don't have to write so much. Here I explain only. 2, 1. X equal to 2, y equal to 1, you get the answer. Okay? So here, you see, you write d over dx. It is very nice for you, even better than that, because here you understand that you look at this expression and you differentiate with respect to x, keeping y unchanged. So you get this answer. And then the same for the other, you see, you have 16 here. That x equal to 2, y equal to 1. substitute to this one, you get the answer. Okay? Similarly, for fy, d over dy is the same expression, understanding that x is a constant. You differentiate with respect to y, you get this answer. Again, if x equal to 2, y equal to 1, substitute to this, you get the answer is 8. No problem, right? But pay attention. You should not write d over dx of this expression. Why? Because d, normal d, is for one variable, and this variable must be x. Here you have function of two variables. You should write curly d. Okay, such a thing. Pay attention. Next, more complicated because more or less this is polynomial. But here, no more polynomial. This is a function psi of u, where u is x over 1 plus y. This is already composite function. And how to work on that? You apply. In general, right? When you have a function psi u derivative at x, you should have cosine u multiplied by u prime, right? And then you get the answer. Then now you apply this chain rule to function of several variables, and you get it, right? So look at that. With the chain rule of one variable, keep y at a constant. How about df over dx? So I can write d over dx psi x over 1 plus y. This is psi u, right? Cosine u multiplied by derivative of this with respect to x, u prime. So you should write d over dx curly of x over 1 plus y. And this one, 1 plus y is a constant, take out. The differentiation of x give you 1. So which means that this only 1 over 1 plus y you obtain together with cosine. So you see cosine and multiply by 1 over 1 plus y. This is df over dx. Okay, so pay attention when you have not so simple form. How about dy? df over dy actually is d over dy again sine of x over 1 of y. First, cosine of u multiplied by u prime, but now your u prime should be derivative of this function x over 1 plus y with respect to y. Not simple u prime, you understand, right? This is already partial derivative with respect to y. That's why you should write d over dy curly of this function. X take out as a constant. You have this one. X and cosine. But how about derivative of y? 1 over 1 plus y. It is 1 over 1 plus y squared multiplied by negative 1, right? Correct? So that's why you get this answer. This answer. So it's done. Example 8. Not too complicated, but you have to pay attention. Very carefully differentiate step by step. How about 3 variable? Partial derivative. Yeah. Example 9 give you the way apply exactly the same, but pay attention on each case. First one, fx. It means d over dx, x sine y plus e3x square root of y squared plus 9z. D over dx means y is a constant. Y is constant. Z is constant. In this case, you see differentiate each term. You should have sine y multiplied by x prime with respect to x, right? But don't write like that, because you write like that, you don't know with respect to what variable. So then it's better for you to write d over dx, because you already take out sine e. d over dx, d over dx, this function plus take out, right? Square root y squared plus 9z. And then d over dx e3x. What is that? This is what? What is that? e3x multiplied by 3x derivative. Then you get the answer. Here, fx, partial derivative. Correct? So you see sine y 3e to power 3x and square root sine y, because this is 1, 3e to power 3x and square root. That I write only answer, and please you train for that. For the other, for this one, you should keep x and z unchanged. Only that and this you should pay attention. And the next one, for derivative with respect to z, all x and y are constant. Only pay attention on z in this case, and you get very nice formula, because x sine y derivative with respect to z gone. It is 0. Only the second term you have. Okay? Do it by yourself and compare with the answer I gave you. The same function here. So you see, this time I have some more time to give you more example. As last year, several students emailed me after thanking my lecture. They expressed the wish that for the next calculus, please, if possible, wherever you can, provide more example for us to understand the situation. And this part, I could do such the thing for you. Many examples up to now. And Several examples you see, I explain, but I don't write how to do. I explain here. You can follow my explanation and then you repeat and try to do by yourself, right? Okay, now fx means d over dx exy logarithmic of z. Constant, but constant here in the power. So this is should be constant take out. And then d over dx exy. And that one first is exy and then multiply by xy derivative with respect to x, which is y. So you have this answer. Okay, that. How about for other? Fy you can do by yourself. X and z keep as constant. Fz, x and y keep as a constant. You work only on z. That is, this one, no z take out. Only derivative of logarithmic of z. You know it is 1 over z. And it is done. Right? Interesting. Good. Now, second partial derivative. What do you mean? You have f, and when you have fx partial derivative, fy partial derivative, they are also function of two variables. They are also a function of two variables. Here, see. Yeah. Partial derivative, two variable. Partial derivative, two variable. Which means a newly obtained function fx, fy subscription, I mean, can be considered as a new function of two variables, and then we can look at the problem or the question of partial derivative, right? Partial derivative of this newly formed function, which means for fi, you can consider d over dx of fx, d over dy of fx, the same d over dx of fy, d over dy of fy. So which means you have more four derivative partial of the first derivative fx and fy, and all these are called partial derivative of second order or second partial derivative. See here, see fx again with respect to x, with respect to y, fy with respect to x, fy with respect to y. They are called second partial derivative of f. We can also use the notation of curly d. But please pay attention. I do hope that for your midterm or final exam, no student will be confusing. Why I say like that? If you use subscription notation, you should go from the right, from the left to the right, which means fxy mean first you take derivative with respect to x. And after that, xy, right? X first and then y. After that, you take derivative with respect to y. Go from the left to the right. But if you use a curly D, then this you have to change the order, which means that you should write d square f over dy over dx, understanding that you go from the right to the left. First, you take derivative with respect to x first, because this is on the right. Yeah, this is the first one. And then you take the second with respect to y. So they are different in writing. Value the same. Reason the same, but writing differently. Either you write in the order. So here order is from left to right. Order is from right to left. Different writing. Okay, pay attention. You see, I write first differentiate with respect to x, then, or we write follow after that, right? Differentiation with respect to y. Okay, pay attention. So this means, as I explained here, you have 4% derivative second. Yeah. For two variable, you have 4 second order partial derivative. Đạo hàm riêng bậc 2 là sẽ có 4 cái. Yeah. xx. You write, in this case, no difference between order. And you should write d square over dx square. Yeah. Square here doesn't mean that square. Square here means that second order. Understand? fxy, x first, y second. So you have this one. fyx, y first, x second. You have this and yy. So such a thing you should pay attention. Okay? So 4. How about 3 variable? 3 variable, you have 9 second order derivative. Or if I give you one function, this one. Yeah. 5 own second order derivative. You should give 9 answer. Do you like it? Maybe not, right? But this case is easy. You can do by yourself. Try to find all 9 answers. Okay? That's the function of 3 variables. You have 9 second order partial derivative. Now back to example 7. How about second order derivative of f? 4 answer, right? First fx and then fy. From here, you have fxx and then fxy. From here, you have fyx and then fyy. So 4 functions you can get. Look at that. Here's the answer. This one differentiate with respect to x. You have fxx, 6x plus 2y cubic. This one, with respect to y again, you have this. Yeah, right? But the first one with respect to y, you get here. And the second with respect to x, you have this one. And you can see 6xy squared, 6xy squared are the same. And then you may ask, is it true that fxy and fyx are the same or not? How? In this case, yes. But in general, here, remember, the order of taking differentiation are different, right? X first, y second, y first, x second. But in this case, you have the same. That's the reason you have a question. Is it true that fxy is fyi? Unfortunately, it is not true. No. You try to have some example to show that they are different. And the question, when is it true? Here, the answer. Under some condition, these two partial derivatives are equal. Or we say equality of mixed derivative. If you have a function, you consider derivative of the first order and mix xy and yx, the second derivative. For derivative you need. No need to talk about x, or y. X and y, of course, are different, right? And if these functions, they are function of two variables on some open domain of R2, continuous, more or less is more important. Then they are different. They are the same. If continuous, then they are the same. And this result discovered by a French mathematician, Clairaut, and then is called Clairaut theorem in 18th century. So now you check it. This case, fx polynomial, fy polynomial, fxy polynomial, fyx polynomial, four function polynomial, then they are all continuous. All continuous everywhere, even on R2. So should be the same. Should be the same. Then you should have this equal to that. See? That's the result of Clairaut theorem, right? I remember last semester when we talk about derivative, I remember once I mentioned about the partial derivative for the second semester, and someone already mentioned this guy, Clairaut. So it means that that student already study, or at least have something in his, the main student, male, not female, in his brain or in his head, that there is such a guy related to partial derivative. Okay? Here, find this one and that one. So you understand, this one means that df over dy first, and then dx of that, right? From the right to the left. But this one means that fz first, and then you take with respect to x, and then you consider with respect to y. For that example 10. See, df over dy first. And then you take d over dz. Df over dy means that z constant, x constant, you have exy multiplied by x. Exy derivative and then multiply by xy derivative with y. This is constant. And after that, you consider the first two already xy constant, only the last one derivative with respect to z, you get what? Similarly, yeah, I already wrote the order of taking differentiation, and you get the answer here. See, here actually you have more derivative already. The third one, right? Okay, so see, after that you get the answer f x z x y. So again, quite many examples for you to train home, not home, you are home already, to train and see whether you can do the right things or not. Right? Now, gradient vector. Gradient vector in several variables. First is a vector formed by partial derivative, which means gradient vector in function of several variables related to its partial derivative and denoted by this one. This is not delta here. This is delta and capital delta, and that's small delta here. You know, right? When we talk about delta epsilon, this is small delta, but this big delta. But that one, you have base and vertex here. Quite normal. But the other direction, base on top, a vertex in bottom. Right? This don't confuse with delta. This is not delta. It called in Greek. Chúng ta dùng toàn là dùng cái tiếng Hy Lạp đúng không? This called nabla. Nabla. That one. Okay? So a nabla here. That one. Base in the top, vertex về bottom. You call nabla. Okay? So by definition, for two variable function, gradient is formed by fx and fy, partial derivative with respect to x and y. This means when you have x, y here, you remember you have the unit vector I, unit vector j, and any vector z here. I write coordinate A and B. This vector z is A multiplied by I plus B multiplied by J. So this, we consider this vector, right, is sum of these two, which is multiple of I and J by A and B. So in gradient, A and B here, partial derivative of f with respect to x and to y. So remember definition 14. a function of three variables, exactly the same. Nabla of f is formed by partial derivative with respect to x, y, and z. That in three variables, I, j, and k. I, j, and k. I here, j here, k here, in three axes. This is definition. So example, you are given this function. How to find gradient vector? Easy. You expand this one and find fx, fy. Done. You get the nabla of f is fx and then fy, which is 2x minus 3 and negative 1, two coordinates of this vector. Okay, so then evaluate it at a point x equal to 1, y equal to negative 1, you substitute. You get the answer. At a point, it is like that. So if you are asked to write this vector where negative 1, negative 1, so you see negative 1 as a coordinate, so you have this negative 1, this negative 1, and the vector here, this gradient vector for question 2. For question 2. But if you have a point negative 1, which means that this point here 1, negative 1, then the gradient vector should be like that from this point, right? And equal to negative 1, negative 1. So here gradient vector. If you want to look at a point on some curve, this curve, this curve, this curve. Okay. Next, gradient vector of that. Yeah, what is that? Nabla of f is fx, fy, fz. The vector with three coordinates. So fx here, fy here, fz here. Then you get the answer. Interesting, right? So in general, if you have a curve, then at a point you can find gradient vector by using the partial derivative. As we study, remember the definition. Okay? So more generally, function of n variable f, x1, x2, xn, n variable, we can have the definition of nabla. Nabla of f, x1, x2, xn is a vector in R2, vector in Rn, f, x1, f, x2, f, xn. Then you get the gradient vector. That's the thing. Or I write df over dx1, df over dx2, df over dxn. This is gradient vector. Okay? Done for today. Now, trend 04. Good. I told you about 05, but 1 minute earlier. It is done for today, which means we already study the continuity and partial derivative. Continuity and partial derivative, right? That one. And next time, we study the chain rule and approximation. Next week. Okay? So, any question? No question?
No, sir.
No? Okay, good. Then see you next week.
Goodbye, teacher.
Yeah, bye-bye.
Teacher.
Goodbye,
Bye-bye.
teacher. Professor.
Bye-bye. Bye-bye.